Hello everybody. We are solving one example to apply what we covered in the previous video on the flow in the pipes and the flow in the wetted wall column. So here we have a trichloroethylene, which is TCA. It's a solvent and it's like an impurity or a pollutant in the wastewater. So this is why we like to take or get rid of it by stripping. From wastewater. We do this using the wetted wall column, like what we see here. We study the stripping of the TCE from water to air at constant temperature. So first, this is an important point that we need to know, that this is a stripping process. So it means that flow is going from the liquid phase to the gas phase. So this is the definition of stripping. So this defines the direction of flow. So it's going to be the same direction in the arrows that we see here in this photo here. So we know the temperature and the pressure. It's 293 Kelvin and the pressure is 1 atmosphere. We know the inner diameter of the column and we know its height Z and the diameter D. And we know the volumetric flow rate of air in the column is 500 centimeter cubes per second. This is for the air, and the water volumetric flow rate is 50 centimeter cubes per second. So I know the volumetric flow rate for both streams, and I know that the density of water is 998.2 Kelvin kilogram per meter cube at the 293 degrees Kelvin. And from this mass flow rate and the volume, we can calculate the the volumetric flow rate and the density, we can calculate the mass flow rate, which is 0.05 kilograms per second. We need to estimate, this is the requirement, or what we need to do is to estimate KL, which is the overall liquid phase mass transfer coefficient for TCE across the liquid and gas phase. So we have mass transfer from the liquid phase to the gas phase, so we need to calculate the overall mass transfer coefficient. If you recall, we did this in chapter 27 when we were discussing the convection or convective mass transfer coefficient between phases. And what we did before was solving the problem given that we have the mass transfer coefficients. In this problem, we will see how to calculate the mass transfer coefficient for the two phases. Water losses by evaporation is negligible, so the amount of water is the same. We don't have any transfer except for the TCA from liquid to gas. I know that the equilibrium relation is or follows Henry's law, which is P equals H multiplied or Hx multiplied by Xa, and we know that Hx is 550 atmospheres. Of course, this is in atmospheres because this is dimensionless, so this has the units of pressure at 293 Kelvin. And I know the diffusion coefficient of TCE in air is 8 times 10 power minus 6, and the binary diffusion coefficient of TCE in water. So this is the diffusivity in the liquid phase. This is the diffusivity in the gas phase. So we know a lot of information, and we need to see now how to proceed. We need to calculate the overall mass transfer coefficient, so I need to calculate the individual mass transfer coefficients. We know that there is a relation between the overall and the individual mass transfer coefficients, and Henry's constant is part of it. So this is something that we know from before. So I listed all the information that we know here, and I tried my best to put all the parameters in the same unit system. So I have here the diameter is in meter, the flow rates are meter cubes, the density of water it's already given, the viscosity of water is in Pascal second, which is in SI units. The diffusion coefficients are already in meter square, I'm sorry. Here I got this information about the density of air, the density of water, the viscosities, and all these parameters. I got them from the appendix, so they are already there, and we saw how to get the values previously. So this is something that we can easily get. So this is the profile that we have. There is a high concentration of the TCE in the liquid phase, and then it transfers to the interface, and then at the interface it goes to the gas phase and goes from the interface side of the gas phase to the bulk of the gas phase. So we will do the calculations twice. We will do the calculations once for the gas phase and once for the liquid phase. So for the gas phase, this is simply a flow inside the pipe. This is a typical case of flow inside the pipe, where we have mass transfer between the pipe inner surface and the bulk of the gas phase. So this is a pure flow in a pipe, and then we will use the equation for flow in the pipe. And if we go back, I think here this is a gas phase case, so we'll use this equation. We need first to check Reynolds number and check if we are going to use this correlation or this correlation. So this is something that we need to check. But in both cases, we have to calculate V infinity. We need to calculate Reynolds number, Schmidt number. So it's already a step that we have to go through. So here I calculated the velocity, which is volumetric flow rate divided by the cross-sectional area. Of course, the cross-sectional area is pi over 4d squared, because this is the normal area to the flow of air. So this is the V infinity. Reynolds number is going to be rho v d over mu, and we substitute with the parameters or the values that we have here, and then we have Reynolds number as 1059. So this is a small value. It's not the value. If we go back to this slide, it does not satisfy this condition. However, it satisfies this condition, and we need to make sure that this condition is satisfied as well to use this relation. So we have to calculate Schmidt number. It's mu over rho d, and of course you have to be really careful here, because we have our calculations here, or we do our calculations here for the gas phase. So this is the density of air, this is viscosity of air, this is the viscosity and density of air, the diffusion coefficient in air. So all of these parameters must be in air, and we have to make sure that the units are homogeneous. So this needs a lot of care while doing this. So we use the laminar formula. You can do the check. The check is valid for the Reynolds multiplied by Schmidt multiplied by L over D. It's valid. So I didn't do it for the sake of time, but you can check it yourself. So for the laminar flow formula, it says that and as I said, we had two shapes, but we already have the Reynolds number and Schmidt number, so we don't need to go for the other shape, which is this. Okay, so this is easier. We have Reynolds number, we have Schmidt number, we just multiply by d over L, so it's easier. So from here we can calculate Sherwood number from this equation, and then from Sherwood number we can calculate Kc, because we know Sherwood is Kc over d over d AB, which is diffusivity in the gas phase. We have the diffusion coefficient, we have everything. So Kc is 1.27 times 10 power minus 3. Of course, this is in the units of meters per second. So this is the gas side. For the this is gas phase mass transfer coefficient, so we use Kg. So Kg is Kc over RT, and this is one other thing that we did in chapter 27 before. So this is just unit conversion. So both are gas phase mass transfer coefficients, but both are with different driving forces. I can use this with concentration difference, and I can use this with pressure difference. So again, you have to be careful with the units. R is 0.082 in liters atmospheres per mole Kelvin. So you have to multiply it by 10 power minus 3 to make it meter cubes atmosphere per mole Kelvin, and then the output is going to be 0.052 gram moles per meter square second atmosphere. So this is Kg. So we are done with this part. For the liquid phase, we will use the weighted well column information. So we need to calculate Reynolds number from this relation that we just saw in the previous video. It's 1594, and then Schmidt number. Again, be careful that we are doing these calculations for the liquid phase. So we have here the viscosity of liquid, we have the diffusion coefficient in the liquid phase, the density of liquid, and of course the mass flow rate is for the liquid. So this is important. So by substituting in the equation, we just substitute with the parameters, make sure that all the parameters are okay, and then you get the value of Sherwood number is 57,212, and from the relation, I know Sherwood number multiplied by D over Z, or Sherwood is KZ over D, so whatever. So you'll get a value of KL, which is 2.54 times 10 power minus 5 meters per second. Now to get the overall mass transfer coefficient, it's going to be just direct substitution in the equation. It's 1 over KL equals 1 over KL, which is the local, multiplied by 1 over H kg. Okay, this is 1 over KL, this is 1 over H kg, and then we get the overall mass transfer coefficient with this value. If you check this value of KL and this value of KL, because before even checking the there is one missing part that I didn't mention here, I'm sorry, which is the value of H. So the H that we have is the H that we let's go back to the problem statement. This H here is Hx, which is in the units of atmosphere. So this Hx is the one that we use because we multiply it by x. But actually what we use in this relation is H that has the units of or that's used with pressure and concentration. And if you go back to the derivation of this equation, it was originally derived from H, not Hx. So we need to get the value of H. So to get the value of H, we say that Pi equals Hx multiplied by Xi, and we know the value of Hx, and we can convert this equation into the form that we are used to by just putting the formula of X. So X is Ca interface divided by, or Ca divided by Cl. Cl is the total liquid concentration. So Hx is equal to, or Hx divided by Cl equals H, which we need to put here. So we need Cl, so Cl is the total liquid concentration. Since we have low concentration, so which is the total number of moles of water and TCE divided by the total volume. But in our case, since this is a low concentration of TCE, so we can assume that it's pure water regarding the total concentration. So it's going to be the density divided by the molecular weight of water. So we know the density of water, we know the molecular weight of water, so we can calculate the value of Cl in gram moles per meter cube, and then from Cl we can substitute in this equation to get H in units of atmosphere meter cubes per kilogram mole. Here, this is again one thing that you need to make sure that the units are homogeneous. So this is the units of this side would be kg multiplied by H in the denominator. So if you multiply these two, you will get meter per second per meter. So it's going to be meter per second. This is regarding H. I'm sorry, I missed this. But again, the value of KL that we see here and the value of KL that we see here are very close, while this is far, the value is far from the overall. And if you calculate the overall mass transfer coefficient resistance in the or mass transfer resistance in the liquid phase, it's going to be 1 over KL, which is the liquid phase resistance. This is the overall resistance, is going to be 95%. So 95% of the resistance is in the liquid phase, which is expected even before we look at the overall. We can see that KL is much smaller than this kg, so it means that the liquid phase resistance is higher. So this is all for this problem. The main point that you have to keep in mind is the using the right parameters for the right equation. This is very, very important. In this problem, we have gas parameters or gas phase parameters, liquid phase parameters. So there is a very, very big chance if you don't pay attention to use a wrong parameter or a parameter in the wrong place. So this is all. Next time we will proceed for the last part, which is mass transfer in packed and fluidized bed. So I'll see you then, inshallah. Goodbye.